That's good, yes.
Okay, thank you. Thanks for correcting my spelling. That's what I get for working at home.
You know, I was using Gmail for the longest time, and Argonne refused to let you use Gmail anymore about a year, I don't know, or so ago. But I haven't got my Outlook. It used to correct my spelling, but it doesn't now. So in moments of quickness, I'm sure I'm sending out emails with misspelled words.
What can you do?
Hi, Karen.
Hi, Amanda. You're out
Hi
in
there.
space there?
What? I'm out in space, yes. The state of my office doesn't bear sharing at the moment.
Simona, do you have a video?
Yes, I do. It's just not on.
Ah, great.
Yeah. Karen, did you get the slides for me? I was having some issues with my email last night in the attachments, so I wanted to make sure they'd come through.
I did. And hopefully I've uploaded everybody's correct slides. And I got everybody's picture off the web. So hopefully everyone is okay with those pictures. Simona, yours is the one I had a hard time finding.
Yeah, I like my privacy.
I've been unable to.
I understand that.
So I followed the link to the Indigo page that has all the various things on it, but I was unable to bring up, like, am I supposed to click on sessions or something to?
Hi, Henry. Hi, Jim.
Hi, good morning.
Sorry, Bob, what was the question?
I followed your link and I get to the Indigo page that lists all the sessions, but I can't look at like the individual session. Karen said to look at your picture or something like that. I can't get at any of that. I'm not.
Yeah, I don't see the pictures either.
It's on your slides. It's on, I put a person, the picture of each person on the slides.
Okay, sounds good.
Hi, Howard. I think I got your correct slide in just in the nick of time.
Great, thanks, Karen.
So, yesterday, I think we're just going to continue this panel like the panel was yesterday. I kind of like that the free flow. And so when we get to the discussions, you know, people can just, unless one person is sort of dominating always talking and not giving other people a chance, then I'll have to come in and do something different. But
why would that ever happen?
Yeah, you can mute them, or as chair, you can remote mute.
Yeah, none of us would ever do that, Karen.
So.
It's nice to see you, Jim. The two halves of my life have completely collided at this meeting.
Yeah, lots of intersections of different things. Yesterday, too, was strange with my former graduate student, you know, talking about something completely different. So.
That's neat.
Yep, I think that's the point.
By the way, I was on another meeting yesterday with Helmut, and he really enjoyed yesterday's session.
What session was that, Karen?
It was like biology, chemistry, and material science panel.
Okay.
Oh, it was really good. There were some very stimulating talks. I didn't expect to attend the whole thing, but I did. So.
So it looks like everybody is looking at the camera except Bob. We have a profile on Bob there.
He's got some distraction.
So just so you know, there's also a YouTube stream. So the number of people connected might be higher than what you see because of the YouTube streaming. So people who aren't talking and just watching might just look at it on this live stream.
I didn't try that yesterday. So, Maurice, what time should we give it a few more minutes, or what should we go ahead and begin?
I would say to give it like 5 minutes.
Okay.
Because we're not in a huge rush, and just people tend to connect just exactly once the time shows up. I mean, I see people connecting right now, so I think we should probably wait till it slows down the rate of connection.
Okay.
I would say to fire at will.
Do what?
Go ahead when you want. I mean, I think we can
Begin?
get going because people will continue to connect, but I think the rate is slow.
Okay. All right, then welcome. We're beginning. This is the LAPPD panel, and I'm going to let some of the panelists here actually tell you what LAPPD is. But let's see, I'm going to share. Okay, can everyone see that? I'm in the wrong, or am I in the right view, or can you see that side thing?
We can see the
You
side.
need to go into full screen,
All right, dang.
right below your cursor, yeah.
Right below my cursor. Okay. Right below my cursor here.
Or maybe that's my cursor. I'm sorry. The image of the screen along the bottom. There's a, to the right.
Right there.
Now,
No.
to the right of that, oh dear, just to the right of that, there's a projector screen.
God, I don't see it.
Next to the minus,
See
there's a
the
projector
slider
screen.
bar, yeah.
There you go.
You could just say.
That's it.
So what are you seeing?
Yeah, okay.
Oh,
Yeah, we still see the whole thing. And
Yeah.
I think you just say from resume
Go
slideshow
ahead,
and it
say
should go
resume slideshow. I
full
think
screen.
doesn't do it.
oh dear.
Yeah.
Weird. Okay.
But you could just use this. I mean, just increase the size with Zoom.
What happens if you turn off presenter view?
Yeah, I think that's a problem. Yeah, that's it.
Okay, so where do I turn off presenter? Right
I
here?
saw it just a moment ago.
Sorry, I did not check this part.
Go to monitors, maybe. Over on the right, Karen, there's a thing that says monitors right at the edge of the ribbon under tell me.
I don't.
If you-
Oh, monitors. Don't use that.
And unclick use preventer view and see if that helps. And then say resume slideshow.
Great. You know what?
I'm out of good suggestions.
That doesn't like to be told what to do.
Okay, here, I'll do something different. Let me stop this for 1 minute. Sorry, somebody can tell a joke.
PDF would work. Save as
Yeah,
PDF.
I think going out and coming back in, you might,
I'm just gonna save it as a PDF and use that. How about that? And share the PDF.
That seems fine. Hopefully nobody had put
when
fancy
you go
animations
into
in.
the PDF, whatever PDF viewer, there might be a menu for view. And then just
Okay,
select full screen.
share. Dang it.
Great.
Okay, so that looks okay, right?
Yes.
It does.
Good.
All right, here we go. Okay, so I'm the moderator. My name is Karen Byram. I'm from Argonne. I was actually also a founding member of LAPPD. Today we have panelists, many of who were a part of the original team. So it was really great that we were able to get all these people. Howard Nicholson, Henry Frisch, Bob Wagner, Mike Pellin, Jim Buckley, Michael Manat, Amanda Weinstein, and Simona Malaise are your panelists. And so how we're going to proceed is Howard and Henry are going to actually introduce LAPPD, and then each panelist, and then they'll also have some slides or have some time to introduce themselves and LAPPD. And then each of the panelists will have 5 minutes to introduce themselves, basically to tell us who they are and why LAPPD worked for their area of expertise. And then we'll open up the panel to questions, and we will try to use the format from yesterday, which was sort of a free form style. And let's take it from there. So I have collected slides from all of the panelists, and now I'm going to cycle through these. And so here we go. So Howard, and you can just say next slide and I'll change it for
Sure,
you.
that's fine. So next slide.
Oh, you didn't want to tell us who you are? You wanted to
It's on the
read
next
that.
slide, Karen.
Oh, it's not updating.
Yeah, it's
Great.
still on the first page.
Okay. Dang.
So maybe don't use full screen. That's
Don't use full screen. How am I using oh, maybe I can do it here. There
well,
you
you're in full screen.
Did that work?
There, yeah.
There you go. Okay. So I'm Howard Nicholson. I'm currently an A&L associate. From 2006 to 2010, I was an IPA in the DOE HEP office. And in 2008, Dennis Kovar, who became the associate director of HEP, moved over from nuclear physics, wanted to make some changes in the way HEP categories were handled. So in particular, he decided to change the KA15 funding category, which is now KA25. But at the time, it was sort of a slush fund mostly for national labs. And he wanted to turn that into a responsible program. So he decided to make a detector R&D program. And he asked me to develop the program from scratch and run it. So at the time, I was completely free to set up and run the program any way I saw fit, subject to Dennis's oversight, who said basically that if he didn't like what I was doing, he'd just fire me. So since considerable directed detector R&D was funded through major projects, I decided that the KA15 program, now KA25, should be primarily directed toward generic detector R&D and should provide considerable funding for high-risk, high-reward detector development, which could have significant impact on current and future HEP programs. So next slide. So at the time that Dennis sort of decided to start up the detector R&D program, the HEP office was just beginning to consider the photomultiplier cost associated with a 100 kiloton water Trankov detector for what was then called the LBNE, the Long Baseline Neutrino Experiment Project. And the cost of photomultipliers was projected to be about $300 million for the 100 kiloton detector. And those phototubes would all have to be procured from Hamamatsu. So a cheaper or higher tech alternative would be very desirable for this particular project. And then in spite of widespread use of photomultiplier tubes in the US, HEP experiments or experiments with US collaborators like Super K, Snow, Xenon 10, Xenon 100, Lux, Auger, Veritas, IceCube, and major contributions to their initial development by RCA, there was almost no remaining US expertise in photomultiplier manufacture in the United States. So there was an interest in the US HEP community in developing very fast photomultipliers for a variety of applications. That's Henry Frisch, and potentially large markets for new photomultiplier technology, including medical imaging and homeland security. And at this point, let me just say that all of the documents, or most of the documents associated with the initial development of the LAPPD project belong to the government. So much of the information that I'm giving you now is based on a few documents which I still have and my recollections of the events at DOE. So if they don't exactly mesh with your recollection, it's because my memory as I get older gets faultier. But I think this is basically correct. Next slide. So at that time, in 2008, 2009, Stephen Chu, who was Secretary of Energy, identified the following priorities for science and discovery by investing in science to achieve transformational discoveries. So in particular, he wanted to connect basic and applied sciences. He wanted to re-energize the national labs as centers of great science and innovation. He wanted to embrace a degree of risk-taking in research and to create an effective mechanism to integrate national laboratory, university, and industrial activities. In addition, President Obama at that time provided stimulus funding, the ARRA funding, which ultimately provided $5 million for LAPP development, in addition to yearly HEP support for detector R&D from the HEP budget. So the point of all this is that there was a real opportunity here to take on a high-risk, high-reward, expensive project which might have significant benefit to the HEP community. There's a sort of a very helpful set of circumstances which made all this possible at DOE. So the next slide. So what I basically did is look around in the community. As I say, the need for photomultipliers, it looked like a large number of photomultipliers for a large Cherenkov detector was a major consideration. And so, so what I did when I started off on this program is I traveled around to the community, trying to identify areas where there was expertise in the areas where we thought there might be some significant opportunity for a major generic R&D project. So Argonne National Laboratory had developed atomic layer deposition, which was suitable for activating capillary arrays into microchannel plates. Ossie Sigmund and his group at Space Sciences at Berkeley had considerable expertise in fabricating photocathodes and some photomultipliers for space programs. Henry Frisch and his group at Chicago had considerable expertise in electronics, and Henry had located a company, namely Incom, which could provide large area glass capillary arrays at reasonable prices. So Argonne, Chicago, Berkeley, Incom, as a collaboration, had the expertise in photocathode fabrication, gain stage fabrication, and electronics readout, which appeared, to me at least, to cover all the necessary bases for photomultiplier development and fabrication. So I encouraged Henry to submit a proposal for funding for a major project, which ultimately became the LAPPD project with Henry as the PI. The proposal was received and sent out for review. There were 4 reviewers. All reviewers had reservations about some technical aspects of the program, but we believed that their concerns were resolvable based on the expertise of the collaboration. However, the group had a lack of expertise in assembling photodetector components into a large workable device. And ultimately, this turned out to be a major stumbling block in the fabrication of a working device for many years. So essentially, this was the launching pad for Henry to set up, run the LAPPD initial collaboration with considerable interest and support from the Office of High Energy Physics. So with that, I'll turn it over to Henry, who can go on from here.
Okay, Henry.
Okay, I just turned off my video because of bandwidth problems. I'll turn it back on, but I may turn it off again if I have bandwidth problems.
We have your picture in the slide, so.
Yeah, you have my picture in the slide. So thank you, Howard, and that was very precise and marvelous, quite frankly. So here's a picture of many, but not all of the players. There's a website, psec.uchicago.edu. And if you go to the document library and look at the list of authors, it's 3 or 4 pages of people who have actually contributed to a written document on this. But we owe it to Howard, as will become clear. Next slide. Or you can see just one quick thing. You can see Howard, you can see Ossie Sigmund, you can see a whole Bob Wagner, you can see a whole bunch of the Karen.
There's Howard, Bob.
There's Howard on the right, and next to Bob, and then Gary Varner, Bernard
me.
Adams, I mean, so forth. And Jean-Francois Janat, particularly, but Ossie's back this door does. So this is just one snapshot. So I took a slightly different tack on my talk. I basically, something in Karen's email said, you know, why did it work, and to what extent is this a model for things? And so I tried to focus on what I thought really actually made things go. And underlying it all is there's an immense strength of talent. There's enormous talent out there. And the question is, can we actually be somehow access it? You know? So that's, but number one was we used leverage. So there was a lot of existing expertise. So we didn't pay a lot of full-time salaries. There was a large leverage on productivity and cost. Similarly, the facilities, that there are facilities many places, and you're not, luckily the base program supports a lot of that. So the question is, can you leverage off of it? This was true at Fermilab, at Argonne, even to some extent at industrial partners, certainly at universities where you can pick up students very cheap. And so there was a lot of Another ingredient of the leverage is it really was a pickup ball game. We weren't organized particularly. We attracted experts as volunteers, and often one found, particularly things like the light source at Argonne, if I can be blunt, underappreciated, underchallenged, and overmanaged people who were delighted to go do something interesting. And so there's immense leverage there too. These are very expert people. And then lastly, and the key thing was the complementary strengths of the national labs, which had marvelous facilities and experts, industry, core competency and experts, income, RMD, and others, and the universities. And I want to feature particularly the technical staff at universities are much underappreciated. We would be no place without, for instance, Mary Heinz of our, who kept all the web pages, just holding us together in some sense. So next slide. So a second thing that really I think worked very well, and Karen and Bob and others were, we had constant, incisive, informed review. And one can ask, how do projects go off the rails? And the answer is a lot of people know it's going off the rails, but somehow it's hard to get in there and change the direction. It's an enormous ship. And people on the deck, they come for a visit, they walk around the deck once and they say, you should do this, because that's what I've always done. And they catch on the plane and they leave. So the committees were formed at the start of the project. The same committee for the life of the project. So people really knew. There was a lot of review. We had 4 committees times 2 meetings a year. That meant that something was always being reviewed. So people were meeting and talking and thinking, are we doing the right thing? You can look at they're written in archive recommendations. You can look at reviews. And last thing, I think most important, it wasn't a confrontational kind of thing. People didn't fly in, read the documentation on the plane, say, do it my way, and fly out again. The committees had critics, experts, competitors, including people from industry who were competing, who didn't want us to see us succeed necessarily, though they did. And internal people who could explain why occasionally non-standard and even crazy directions were the right things, even if they weren't the usual. So I look at big projects in HEP, and I would recommend strongly this kind of review. It doesn't have to replace other reviews, but somehow having the people inside who can say, you know, I just don't think this is going well. And can talk about it. And so this was very important to us. And Karen and Bob, as I say, we had very good, Gary Varner on the electronic. Next. So we had visionary, sophisticated agency support. That continues with Helmut, by the way. We're talking about the beginning here. But Howard, as he said, and he described that very well, he looked at this one review that said that, we didn't know what we were doing. And it may have been correct, but he decided there was no fundamental reason that it wouldn't work. It was just we didn't know what we were doing. And he went ahead. And the last was this blind, stupid, undeserved luck. We hit the 2009 stimulus, okay? So that there was funding. Next. But a key thing is we're not yet done because the goal was to make them in large quantities and cheap. And my claim is they can be very cheap. The components, the main cost is the MCPs, and my guess, and Michael Mina can comment, but I think in large quantities, in real industrial production, it's less than 2K per module. We wrote a proposal to Fermilab for this stimulus, 4 years and $1.25 million a year to provide a bridge to industry. What is needed here, it's a step that is missing with SBIRs and such. The step is to make something a commodity, so you can buy large quantities of it cheap. Incom has done very well with SBIRs. They've done very well generally. They can make small numbers of very nice tubes. But the question is, how can you make 100 a week? And we have filed a patent for this, where I think we've developed every step of this. But it needs a bridge. It needs something on the order of $5 million for the next step. And I realized in writing this, our proposal was to be done at Fermilab. It's less than 4 people for 4 years at 1.25 million a year. But it could also be a contract. This could be a contract to Incom or to some other company. And this is a picture on the left of the in situ, a stack of 3. On the right is 6 tables of 18 modules each. That would 6 tables at 18 per table is 100 a week. So this is let's try the end. Next slide. Oh yeah, and just to show you this isn't idiocy, this was what Howard referred to at the time of Dussel. We actually had a company make a proposal. They had the equipment and they had the expertise. So this is a real proposal. And they were going to make some very large number, and I can't remember whether it was 20,000 or 50,000 or 100,000, but they were going to make a lot, and they were very enthusiastic. Unfortunately, Dussel went down, and they pulled out immediately. But this is just to show you that a company that made a very similar object, it wasn't microchannel plate based, but it was a sealed vacuum tube of this size, was willing to make a real proposal for this. So this is not nuts. But this is the step that is missing, and I really think that we will have failed, and I mean failure, if we can't do this, if we can't get it to the point where they're cheap and plentiful. If they're expensive and boutique, one at a time, it's a wonderful device, but it will never be what we need. And the medical imaging is the big thing. We just actually filed a patent for whole body scanning, PET scanning, at least a factor of 100 lower dose, which is a game changer for serological and for COVID-19 and other diagnoses. But you don't do it if you've got only handfuls and they're expensive. Yeah, I think that's the end, Karen, but there were 2 slides that I didn't include. Oh yeah, so I just want to say that this was a marvelous group. I want to thank everybody. This was really fun. 2 of the key people are not with us anymore. Anatoly was just always so important. Here he's holding a chalice for the photocathode development. Anatoly's Fermilab, but he's at Argonne with the photocathode piece. Bob Metz was our beloved machinist who would listen to us and then quietly go away and come back 5 minutes later with whatever we needed. So, and there were 2 slides I just wanted to flash.
So I had then you had backup, and so I moved all your backup slides.
Okay, that's fine. There were 2 other things that were important, but they largely just said, pick something that's going to go, that there's no reason why it can't go, and find the very best people you can. And that's what the last 2. So I want to thank everybody. That was fun, but we're not there yet.
Okay, so now now we're going to move to the remainder. So Bob and Howard introduced LAPPD, and so it's been 20 minutes in introduction. So now we really want to keep the introduction to 5 minutes so that we can get to the panel discussion with the questions. So Bob?
Okay, Karen, I'll depend on you to keep me to 5 minutes and just cut me off. So one thing is, if you're seeing my video, I may look like I'm in a very funny place. I'm in our 3D printer lab. We keep the UV light out because we have UV sensitive photoresins. And this is a continuation of the project. We're now trying to 3D print microchannel plates. But to get into my background and motivation for working on LAPPD. So I guess we were supposed to introduce ourselves, and I summarized my career in 4 bullet points. I came to Argonne as a postdoc back in the late 70s. Nobody ever told me to leave, so I didn't. And I came as to work with the polarized proton group that did polarized proton, and proton neutron scattering. And that was about 3 years, and mainly working with multi-wire chambers, scintillation counters, and cryostats. And then I moved over to CDF, where I spent basically my career. It was 25 years. Amazing length of time for an experiment, and worked on electroweak couplings. But I was responsible for basically 25 years for taking care of the central EM calorimeter phototubes. And then in the early 2000s, transitioned over to Veritas, and then we had a small Cherenkov telescope at Argonne called TRICE. They were looking for gamma rays coming into the upper atmosphere, and that was sort of 5 years. Mainly it was for my part looking for indirect dark matter in halo dwarf galaxies, and then again concentrating on phototubes and getting into silicon photomultipliers with an interest of trying to adapt the fine pixelization of silicon photomultipliers into a camera for a gamma ray telescope. And then that transitioned into LAPPD, which was sort of a 11-year project for me. I came in as the project scientist and did photodetector fabrication and a lot of management. And got to work on ALD and photocathodes, sealing and vacuum systems, the whole thing. It was a fun project getting your hands on something. So my motivation was, at the time I had been working on developing silicon photomultipliers for imaging Cherenkov telescopes and timing resolution. Measurements carried out alongside of what was happening at Argonne, which was Henry and Karen's project for trying to achieve picosecond timing. And we had a small laser setup that where a lot of the work was done. And Camden Ertley, who was an undergraduate at the time and has progressed to these days, and actually worked at INCOM and will be, I think, leaving there soon. For me, it was particle ID using timing was certainly relevant from CDF days and of interest for the coming LHC. And also the ability to do millimeter resolution on individual photon detection, which is useful for both time of flight and Cherenkov. And the idea came up of, if you had a large area picosecond photodetector, you could instrument a gamma ray telescope camera with just a handful of these. But probably mainly how I got into it was they required a project scientist, and Harry Wirtz at the time was our division director, and he asked me to take responsibility, and I did. So, but what I've outlined there in red still are the HEP motivations for LAPPD. So, Karen, next slide.
Okay, so 4 minutes you've taken.
4 minutes. Okay, so I have 1 minute. So there's I'll just spend the time on this and skip the last slide so people can correct my any errors I made. As Howard had pointed out, there were 4 challenges here. We had to develop gain with a borosilicate glass capillary array functionalized by atomic layer deposition, fabricate large area photocathodes, seal the MCP and photocathode in ultra high vacuum, and make it permanent, and then develop fast electronics. And all of those seemed very challenging, except for sealing seemed to be fairly well in hand. SSL, Space Science Lab, Ozzy had sealed these devices on a smaller scale and ceramic package for a number of years. But this turned out to be the hardest task, and it took years to achieve a hermetic ceramic package, and INCOM is now doing that routinely. And the indium solder seal was very challenging, but INCOM again, along with Henry's group, they've now made that sort of a standard technique. Here at Argonne, Dean Walters and Mark Kupfer, Dean was a vacuum engineer, Marco as a grad student at the University of Illinois, Chicago. They developed an alternative technique, which was a thermal pressure indium seal. So you just smashed indium to make the seal, heated it up, not to melting, but just heated it up enough. And that made a permanent, very good seal. And that's still what we use at Argonne. It's not the general means. It does take a little more effort. But, you know, it was interesting that what we thought would be the most straightforward turned out to be the hardest. So I'll stop there because my time is probably up, and you can just flash the other slide if you want, or people can look at it.
Okay, so now on to Mike.
Yeah, oh, a younger Mike picture, but okay. Yeah, I'm an Argonne Distinguished Fellow. I'm a surface scientist, and our connections to the, and occasionally a division director and assistant division director and things like that, that I try not to do. But we worked with Henry Wirtz and had a good friendship, actually, and we were exploring several places where fundamental science and capabilities that were developed under basic energy science and material science funding in the material science division could be applied to HEP problems and opportunities. And so that comes from really understanding what the problems are and understanding what the capabilities are. You know, just two examples were superconducting RF cavities and understanding how surface finish can really change the ability of cavities to operate, and superconducting detectors, which are being used at the South Pole Telescope now. In this project, we had expertise in surface science. I'm a surface chemist. Energetic particle interactions with surfaces, which I'll show you are sort of the key to making detectors work, and the chemical coating of the interior surfaces of high aspect ratio materials, which, you know, in a general physical way of coating just wouldn't happen on channel plates, because you couldn't uniformly coat these pores, which have high aspect ratios. That is, they got small openings and they're long. And so you just get no material into them. And so if you go to the next slide, Karen, we can show sort of how this works. Energetic particle interactions for surfaces are sort of the key. You know, energetic particles like electrons or ions have to hit the surface of the channel plate. And when they do, secondary electrons are ejected. Understanding that process and what makes large numbers of secondary electrons be ejected and what doesn't is sort of the key to making a channel plate work. And we have a long history with that, and a lot of fundamental discoveries in that area were produced by research in this area. Of course, the reason we did it wasn't to make channel plates better, but because sputtering is a key way to do analytical science, secondary ion mass spectrometry, for instance, and a key way to make integrated circuits. The thing you have to recognize is that channel plates also need a surface which gives high secondary electron yield, but they have to be stable and high resistive conductors in order that we can bias them in a way to make them work. In the area of energetic particles interactions with surfaces, we have a lot of the fundamental discoveries in that area and understand how erosion happens in these detectors and how secondary electrons are produced. Go to the next slide, last slide. The other capability crucial for LIDPD was the ability to functionalize and coat the interior of pores. And with Jeff Elam as a postdoc and then as a scientist at Argonne, we have developed atomic layer deposition, which is a chemical coating method akin to MOCVD, but where we separate the two chemicals in a way that we can produce atomic coatings with atomic layer precision. And those coatings can be a wide variety of materials. And so you can see that we can produce we can produce coatings which are uniform in thickness, even if the pores are kind of rough, and produce them without any defects or with very few pinhole defects. That capability to coat even nanoporosity down to levels where the pores are just a few nanometers in diameter was something which we developed through BES Math-Sci for catalytic materials, but recognized that these are hugely important for making detectors like channel plates. And so that's sort of where we were. And I think we were looking basically for ways to broaden and use this technology to have an impact on science in general in the US and on capabilities. So I think that's the last slide, and I'll stop here, hopefully 5 minutes.
Oh yeah, no, you did 4 minutes, great.
Oh, okay.
Okay, Jim?
Okay, I do way too many things, but I think my role in this project was, first of all, being a skeptic, but Howard and Henry, being very open-minded people, kind of brought me in for my expertise, which is this center bit here, the gallium nitride detector. So we had some expertise in photocathode growth, and what we were doing was growing kind of atomically tailored heterostructures of aluminum nitride, gallium nitride, indium nitride. And we were achieving, very high quantum efficiencies, mostly in the UV. And then my colleague, Dan Leopold, who also passed away several years ago, tragically, he and I think, kind of played a role of built-in reviewers, and we helped. I think I'm just a naturally critical person, so, but with good intentions. So I think that was our main role. And then I kind of moved away from the project, getting more interested in low radioactive background liquid xenon detector development. And that was quite productive, but a lone university group, we've honestly had trouble pulling off making complete sealed tube devices, because as this group showed, that's a big challenge. Anyways, I'm coming back again, though, to talking to Bob and other people, because I've also, as a spinoff, gotten involved in a project in biophysics and fluorescence lifetime imaging, where we're interested in using microchannel plates and kind of a slightly different anode structure with a bunch of high-speed FADCs and stuff to do both imaging and fluorescence lifetime in biological systems. And I continue to work on them. UV photodetectors. But I should say that I'm now really shifting. I've worked in gamma ray astronomy, dark matter stuff. I briefly had a little short involvement in LZ, but I've really settled in on ADMX now. So I've completely shifted gears to working on kind of superconducting quantum limited cold electronics and things like that. And I actually see a place where nitride semiconductors, niobium titanium nitride, could play a role in both high quality factor cavity coatings and even parametric amplifiers that could work in high field using kinetic inductance and stuff like that. So weirdly, this nitride semiconductor growth has kept me involved in various things. So I think I'll stop there. You can look at too many other things I'm doing.
Thank you, Jim. Okay, Michael?
Yes, so good morning. My name is Michael Minot. I'm with Incom Incorporated in Charlton, Massachusetts, and we are the firm that was designated to commercialize LAPPD. My 3 slides are in one way a snapshot of current performance, but this is not a technology review so much as an opportunity to show how the multidisciplined approach can solve a problem. So I'll be pointing to some of the results and underscore the benefits of involving industry at the beginning, and why it was important for Incom to be involved at the beginning. Personally, my own background as a chemist and materials scientist and a glass technologist was actually key to my involvement, as well as that of Incom Incorporated. So if we go to some of these characteristic features, the large area planar design, there was a lot borrowed in the early days from what was going on in the, believe it or not, television display market. And in fact, our use of fritz sealing and the pin-free concept of having conductive traces pass underneath the sidewalls was sort of borrowed from what we were seeing being done in the display market. The high gain that we're able to achieve with these detectors comes directly from the ALD technology that Mike Pellin and Bob Wagner referred to, and the magnesium oxide coatings that are used. Of course, the photocathode performance, which is now state-of-the-art over large areas, is fundamentally, chemical processing. And I'll jump to the low cost and come back to the time resolution. The point about the low cost is this is not about manufacturers slitting their wrist in a drive to lower price to feed at the bottom. The low price of the LAPPD is designed in based on some of the technologies that were incorporated and some of which were stipulated very early on by the core team. And so the Borafloat glass, the Incom's hollow core strategy for making the glass substrates, the pin-free design goes right to the yield. And now we're beginning to see a lot of activity that I won't have time to talk about for onboard readout electronics, which from a system point of view are very, very compelling. So, and low cost, I can't help but remember Henry's mandate of a frugal photo detector. So that's absolutely where we're going. So next slide, please. So it wouldn't be a picosecond photo detector if we weren't down in the single picosecond numbers, which this is fairly recent data, but not quite the full fruition of what Henry was predicting, but we're converging on it. And I think that Henry deserves a lot of credit for not just the vision of a picosecond photo detector, but the vision for transforming the way people designed their experiments, knowing that they could have picosecond timing at a reasonably cost-effective price. And the fact that we're now beginning to see that in our sealed detectors, this work was done at INFN in Bologna, Italy. And it's a curious result. It is specific to the particular set points, but it's also for an LAPPD with 20 micron pores. So we have every bit of expectation that the results will get better even from here. The final slide speaks to the application space. And again, not just to show that we've got 20 LAPPD under test in a variety of early adopter communities. But now what was driven by the LAPPD consortium continues to be driven forward by what we like to call the pull of the customer. So the product is continuing to evolve, and it's in different markets. Of course, it's HEP and nuclear physics, but as Henry pointed out, we've got two collaborators, including UC Davis, who are preeminent in the PET area, looking at LAPPD for PET. And you'll also see reference to the readout board work. So this is electronic work going on at NALU Scientific in Honolulu, and also Ultralytics, a small company that are developing dedicated readout boards that'll sit on the backside of the LAPPD. And this is going in the direction of reducing the wiring load at these large HEP and nuclear experimental sites and speeding the transfer of data. So it's very, very important in the broader sense. And with that, I'll conclude.
Okay, thank you. So now we're going to go to the last two panelists who are actually users of these LAPPDs. Amanda?
Hi, Karen. Thank you. So my name is Amanda Weinstein. I'm an associate professor at Iowa State University. I am a particle astrophysicist who works on a variety of different detectors that either incorporate high energy physics technology, like Veritas. And I should note that I'm actually the third person on this panel to speak so far with an involvement in that experiment, but also with detectors that doing particle astrophysics by piggybacking onto high energy physics detectors, especially neutrino detectors that have other purposes as well. And I became involved with Annie somewhere between 5 or 6 years ago. And Annie is a gadolinium loaded water Cherenkov detector that operates off the booster neutrino beam at Fermilab. Its primary physics goal is the characterization of neutron abundance in the final state for neutrino nucleus interactions. But its other major purpose is as an R&D platform for new neutrino detection technologies and methods. And in particular, it focuses on both novel detection media, hence the gadolinium loaded water, and also the fast photo sensors. And Annie's connection to LAPPDs has been there from the very, very beginning. I would actually point out that there's proof of that connection, because if you look carefully at some of Henry's slides and the footer at the bottom, they were clearly adapted from the Annie first collaboration meeting. And the purpose all along has been that there are two components to the events that we're looking at. And in order to get the information about the neutrino interaction vertex, we need to do a good job of reconstructing the momentum and energy of the associated muon. Now, the LAPPDs, because we're getting that information from the Cherenkov light from that muon, the improved spatial and angular resolution means we can do a much better job of reconstructing that momentum and energy. And in addition, which the lower plot on the right shows here, you can see the impact of adding 5 LAPPDs to the Annie detector in terms of the improvement in the vertex resolution. And we can actually reconstruct the vertex to a few tens of centimeters by adding those LAPPDs. And that's difficult to do in water. Now, an image of the Annie detector, by the way, is shown in the upper right. One of the things that I wanted to comment on is that when I first joined Annie, I was actually recruited to work on the electronics, both the trigger and the data acquisition electronics for the other aspect of Annie, the photomultiplier tubes that help us detect light from the neutron capture aspect of the event. My role in Annie has evolved over time, and in 2020, I actually took over management of the LAPPD project. Next slide, please. So my role as LAPPD manager is multifold. One aspect of my role is to oversee the process of characterizing the LAPPDs, both in terms of their quantum efficiency and uniformity, but also in terms of their position resolution and their timing performance and gain uniformity. And I wanted to show that this photograph in the upper left, which shows the first batch of 5 LAPPDs that we received from INCOM, and we've been working extremely closely with INCOM all along. We now actually have 6 LAPPDs in hand, one of which is a replacement for the second LAPPD on the left, LAPPD31, and that has been replaced with LAPP63. By the way, Michael didn't say it, but there's a photo of the replacement LAPPD63 in his slides, along with a map of its quantum efficiency. In the lower right is a map of the quantum efficiency for one of the other tiles, LAPPD39. 4 of the 5 LAPPDs that we have, including LAPPC63, actually have quantum efficiencies in excess of 16% and are extremely uniform. 3 of those actually have quantum efficiencies in excess of 20%. So INCOM has done a really great job of working with us to make sure that we have photosensors that meet the spec we need for the experiment. Other aspects of my role directly focus on the technical challenges that we have to meet in order to operate ANI as we want. One of these is commissioning the custom electronics that have been designed for the LAPPD readout. In particular, over the past year, there's been a lot of work on firmware development. You can see those electronics sitting on top of an LAPPD inside of a waterproof housing on the right. Another aspect is to make sure that we can deploy both the LAPPDs and that custom readout chain safely in water. And so that's been a big effort over the past year. And finally, the last challenge that we have to meet is to understand how to most effectively use the data from the LAPPDs in a blended experiment that uses both conventional and fast photosensors. Next slide, please.
Okay, you're at 6 minutes now.
Oops. Well, in that case, what I will just comment on is that we have a beam commission detector, and we're in the process right now of the final characterization and integration of the first one of these LAPDs with the readout electronics at Fermilab, and the deployment of that first LAPPD in water is imminent.
Great. Okay, thank you, Amanda. And Simona.
Oh, my name is Simona Malace. I am staff scientist at Jefferson Lab since 2017. Some of my responsibilities at JLab, I measure the beam polarization as delivered by the CBUF accelerator for one of the experimental halls, one of the 4 experimental halls at the lab. I am responsible for various detector systems like the trigger hodoscope system in Hall C. Occasionally, I am leading bench tests and in-beam detector tests. I am an online and offline analysis expert, so I participate in the setup and running of experiments in Hall C in particular. And I coordinate experimental runs often, and I have my own proposals that I get approved, and I run my own experiments at the lab. Next slide. So my interest in LAPPDs came via SOLID. SOLID stands for Solenoidal Large Intensity Device. It's a complex apparatus that was proposed by a very dynamical and enthusiastic collaboration formed by scientists from JLab, other labs, and universities to basically study a variety of physics topics. I listed some on my slide, but it's not an exhaustive list. So SOLID is at the stage of conceptual design. It's not, it costs quite a bit of money, so we have to get funding from DOE to build it and run it. It's not a DOE project yet, but it passed the Jefferson Lab director reviews, and we are scheduled for a DOE science review next March. The hope is that SOLID will become a DOE project, and it will and we will get funding to build it and run it. So part of SOLID, we have two Cherenkov detectors, light gas and the heavy gas Cherenkov detector. The baseline photon detector option we have right now are multi-anode PMTs. The region in SOLID where the photon detector in the Cherenkovs would be installed has high magnetic field, like around 100 Gauss. Hence the MAPMT choice initially. We have to balance the cost with the need for a very good collection efficiency. So we have to tile several multi-anode PMTs to basically ensure that we have very good collection efficiency of the Cherenkov photons. But we also have to keep the tile small enough so that we can make SOLID cost effective. Lately, well, not lately, for some time, we have been exploring the option of using LAPPDs as a photon detector instead of multi-anode PMTs. And we like it because it's resistant in magnetic field and it's cost effective, and it eliminates the need of tiling multi-anode PMTs, and we don't have to use these cones that ensure good collection efficiency. And obviously, we don't have to worry about, like I said, shielding it from a magnetic field. Next slide. So there was a pre-R&D submitted to get funding from DOE to run an in-beam test at Jefferson Lab. That would we wanted to test the two options, the MAPMT and the LAPPD option for SOLID in an electron beam environment at JLab. And we've done that starting with March this year. We ended the beam tests in September of this year. The LAPPD was tested last in a succession of tests we've done. So what you see in the bigger picture is the test stand. There are two platforms, and then at the very top it's a detector package. We had scintillators and calorimeter to form a trigger, an electron trigger. And then there was the tank, the Cherenkov tank with various gases in it. We used CO2 and C4F8. In the end, we also had nitrogen available. And at the top of the tank, I don't know if you can see my cursor, there is a box. In that box, we had basically the photon detector. Initially MAPMTs and then the LAPPD. We swapped the box out. The LAPPD came from INCOM. The quantum efficiency was around 16%. We used the LAPPD 38. We are still working on analyzing the data, so we basically want to compare the two results from MAPMTs and LAPPDs. What I'm showing here in the plot is, I guess, an ADC spectrum of the LAPPD signal when we sum over all 64 pixels of the LAPPD. And different colors represent the different gases or different levels of filling the tank with a particular gas. So I'm not showing a calibration in terms of photoelectrons. We weren't able to identify the single photoelectron with the beam data. We did have very long signal cables running from the LAPPD itself to the rack that had the DAQ crate in it, 100-meter cables. So there is a follow-up bench test I'm working on right now. INCOM was very kind to extend the loan of this LAPPD to allow me to run this test. I guess the idea is to test the LAPPD, see if I can identify the single photoelectron, do a high voltage scan, just get a feel for it. And then we can use this bench test to basically calibrate the beam data. And that's what I have.
Okay, thank you. I think that's that's all for the presentation. I'm going to stop sharing here. So thank you, panelists. So you can see LAPPD was chosen for a panel topic, a multidisciplinary group of scientists coming together to solve a problem, you know, that with a successful outcome. And now you can see it in the field. And so we have some questions. So I think, you know, I had a series of questions that, let's see if I can, that we had put together as the organizing committee. I think Henry actually addressed some of these. How well did the, you know, how did the collaboration come together? And Howard addressed the interactions with the funding agency. So I think maybe we can begin with some of the questions in the chat window here. And there's a list. So I guess the first one is, can you comment on the factors that affected the performance after exposure to radiation? And at this point, I think we'll just let it be free, and someone from the panel who feels like they can answer that question.
Well, I'm not sure that we've got a lot of tests where they've been exposed to radiation, but to the limited degree where there have been, and some were discussed last week at the IEEE Boston meeting. In fact, Hamamatsu did a comparison for a PET application where they compared a conventional lead oxide microchannel, a PMT, an MCP photomultiplier using a conventional lead oxide based microchannel plate to what they're now doing, basically same technology that they're copying from us, which is the borosilicate based substrate. And they show that in the case of the borosilicate glass substrate, the signals are much cleaner without certain side peaks that they depicted in their showing of what they were getting with the conventional microchannel plate.
Okay.
I have one comment I just wanted to add, which is silicon PMs seem to have substantial problems with radiation damage and their dark currents going up. And this is proving very challenging for applications in space or in accelerator experiments. In some cases, you can deal with higher dark currents, which go up by orders of magnitude. But in other experiments, you really can't. And I think that's just one more point how the old photomultiplier tube, the old vacuum technology is hard to beat. So just wanted to add that.
Okay, thank you. So here is another, so were the technical challenges bigger, smaller, or about the same as expected? And in hindsight, what would you have done differently?
So what I would have done differently, this is Bob Wagner. I guess from having managed the project, I came into it learning project management by getting just thrown into it. And I think it would have been better to have someone better trained or provide that training. And also, I think looking at large HEP experiments these days, they're very well planned out. And I think we were less planned out. And if I went back, I would try to have a better laid out plan to execute. Henry was very good at guiding the project, and one thing he didn't mention as a part of his mantras was to fail fast. And so we did, we had a lot of failures, and it's good to find out quickly what does not work. As far as technical challenges being bigger or smaller, about the same, it was somewhat surprising that the ALD went forward as quickly as it did, especially for me. Maybe Mike Helen would have a different opinion on that, but that was fairly straightforward. As it's been pointed out both by, I think, Howard and me, the sealing in this glass package, or in any sort of package, that was to us, it was not expected, and that was a bigger challenge than I think we ever expected.
Go ahead, Michael.
Karen, you know, here in New England, everybody's got a different prescription for how to boil a lobster. And a lot of people start with cold water and the lobster's not fighting, and they gently raise the temperature. And that seemed about symptomatic of the way INCOM got into this. We started with our core technology in the glass field, making the substrates for the ALD. And as time went on, we not only bought into supplying the glass substrates, but licensed the ALD technology. And then when that big manufacturer that Henry alluded to didn't step forward, we felt like we had microchannel plates, but without an outlet. So we took on making the LAPPD. And we did it with a lot of naivete and frankly, no background in ultra high vacuum, no background in photocathode deposition, certainly no background in regular production of fully coated MCPs. And it was largely through the continued support of the collaboration and also our funding agencies and our program managers that we have been able to bring on the personnel, many of whom you know, were already known to the collaboration and joined us as employees. And that includes people like Alexei Lyashenko, who was referred to us by Henry, and Camden Ertley, who now is sadly leaving, but has made his mark at INCOM.
So, so if somebody has a hand raised, they're called the Research Center. Who is that?
Yeah, that's me. I've not, my picture interferes, the video interferes with my audio, so I can undo it. But I just, with respect to the ALD, I just wanted to mention one very important piece.
Yeah, your video.
Unsung hero. Neil
You should
Sullivan
turn
of
off your video.
And Anton Trempston. This was very early. Anton told me he was working with irradiance, the magnesium oxide, and the making of microchannel plates. And Neil's recipes actually have, that was really a basis of confidence that it was going to work. So I just want to make sure Neil's not forgotten in all of this.
Karen, let me
I was
just.
wondering if I can, just because my name was mentioned, is that, you know, I'm an optimist, and we believed atomic layer deposition would work for this all along, and really had no worries about it, except that, you know, these are chemistry synthesis. And it takes some time to develop chemistry synthesis. But once it's developed, it's repeatable over and over again. And I think that that's what makes it a commercial way to do this.
It seems to me it's the marriage of the material science and knowing that that was possible and could be applied to the problem, you know, that it was a tool that HEP needed, that somehow the meeting up of your expertise with the, you know, the problem in HEP, that was kind of crucial early on to begin this pathway too.
Aaron, let me make a comment. I think that the major failing from my part was not recognizing the fact that we needed somebody that had expertise in doing the whole process to put together a complete photo detector early on in the experiment. We didn't have somebody who was familiar with fabrication issues and so forth. And that cost us a lot of time and a lot of money. So as I say, in retrospect, I think that we had the photocathode pretty well taken care of. We had the gain pretty well taken care of in the electronics, but we did not have the fabrication taken care of with the necessary expertise. And that's ultimately where we spent a lot of time and spent a lot of money trying to fix that.
Okay, so
So-
I have another question here. Since this project was largely seeded by volunteers and the combined team experience was quite senior with the funding agency track records, do you have any advice for younger people who might also look to work in a multidisciplinary collaboration?
I'd like to comment on this a little bit. My recollection is, a fairly substantial amount of money went to get this started at Argonne. It was like $8 million or something like that. And in terms of volunteers, I'm a fierce advocate for university groups, as Howard and other people know. What was challenging to me, and one of the reasons I was a doubter in the beginning was, so I think this was Kim's question, was how does a university group play a role more than just using the national lab facilities? And that was a challenge. And, we got some funding thanks to, Howard and other people to join in, and we did make progress, but we developed, some kind of fundamental things. But I think I'd turn Kim's question around and say, I think Kim is at Wisconsin or something. How does a young person at a university group participate and do things in that university group with students, hands-on kind of work? That's my question. So I'll turn it around.
So Jim, let me make a comment. I think for very large projects like the LAPPD, DOE requires that it be managed at a lab. I think they're very reluctant to turn over a major project to a university. So the management basically was set up at a lab. I think that there are lots of opportunities for people everywhere in the universities, in the labs, and in industry, if they're interested, to get involved in coming up with an idea which can be submitted for generic detector R&D. The thing that concerns me about this project, and it's always concerned me, is that basically when I started the program at DOE, I fundamentally made all the decisions about how to spend most of the discretionary money. And I don't think that's the right model. I think the model should be the CPAD model, where people in CPAD think, generally speaking, about what big projects they would like to see happen, and then through CPAD try to take these ideas to DOE management as a way of going forward. So a young person at a university has a good idea, should run it through CPAD and get support from CPAD, and then try to get some basic funding support through the DOE programs. But otherwise, you rely on either top-down ideas, or you rely on one or a small number of people that have access to money to try to make these decisions. And I don't think that's the best way to do it.
So if I could comment a little bit from the end user perspective, I think this is also where networking becomes very, very important. I think if you have a good working relationship with the laboratories that are involved in the type of multidisciplinary work you want to do, and you can build those relationships as a junior person, then you are in a position to actually put forward ideas either for a multidisciplinary project, or as we did with Annie, for applications of that multidisciplinary project. and have a lot of that effort based in the universities, even though there's a strong relationship with and a lot of activity at the laboratory as well. And that's in fact how we've kept things going this last year despite the pandemic. A lot of development work on the LAPPDs has been happening at universities within the US and overseas. And we've been coordinating and bringing it together at Fermilab. But a lot of it has had to be done in a distributed way, and that's been true to some extent all along.
So Ian has a question, has his hand up.
Yes, hello everybody. So I was always very impressed and excited by LAPPD, and I think what we're hearing today is wonderfully, it's a celebration of what's been achieved so far, but also is an opportunity for many of us that weren't directly involved to learn more about this model. And I like to comment on what Howard said. Howard and I had the privilege of essentially working for Howard. He was my DOE contract manager when I was a professor at Purdue, and he was a person who understood how instrumentation is the great enabler, and LAPPDs are part of that. And he pointed out just now that CPAD would be a wonderful way for the community to develop ideas, and then through the CPAD organization, pass those to the DOE and also possibly to the NSF as well in some cases. And so I'd like to say that this is something that's been on many of our minds for a long, long time. And recently, I had the privilege, along with Bonnie Fleming of Yale, to be invited by Howard's successor, Helmut Mosiski, to chair the DOE BRN on detector R&D in HEP. And one of the recommendations in that, well, it's not really recommendations, it's observations, is that this type of model that Howard is talking about would actually be very effective. And in addition, I'm now a co-chair of the European Strategy Group's development of a detector plan for particle physics in Europe. And we're having exactly the same discussions there. And so it's a wonderful idea. And I really hope that we can help to take it forward with our colleagues at the agencies, both in the US and also on this side of the pond as well. So thank you for raising that again, Howard. I remember you always mentioned this to me from way back when we collaborated. And I'm glad you still believe it's the right path. I share your view on that. And I know that the Marcel Madomato and I had the privilege of being CPAD leaders for a long time, but we've now passed the torch to two wonderful people, Petra and Karsten, Petra Merkel at Fermilab and Karsten Hieger at Yale. And so they will also pick up the baton here, and I'm sure it would be good if you and Helmut maybe chatted to them about this option. I know that Helmut has very similar thoughts to you, but I think he's online and he should be speaking directly from his observations. But thank you, Howard, and thanks to everyone on the LAPPD panel for what you've done.
Okay, so I think that kind of leads nicely into this next question by Jim Fast. And do you think there was a downside to relying on existing research grant funding? And wouldn't this bias against people outside of HEP and labs who don't have existing KA25, that's the detector R&D support, to participate?
So Karen, if you look farther down, Hari has a comment on that, you know, it wasn't necessarily the existing research grant funding, and as Henry had pointed out, you know, we had this lucky happenstance that there was Recovery Act funding at the time, and that supported the project until that ended, and then it was research grant funding. One thing I didn't point out well enough, I think, in my slides was it was absolutely necessary to have this multidisciplinary approach to make LAPPD work. We really relied on facilities and expertise of people in material science and chemistry and that. And it was fortunate that DOE was willing to fund support of people outside HEP to bring this expertise, and that's where I would encourage the Office of High Energy Physics in terms of K-25 funding, that it shouldn't be shy about using that money to support facilities and people outside HEP also that are contributing to these projects with necessary expertise.
You okay, Michael?
Well, one shouldn't underestimate also the impact of SBIR funding. I know that by its nature, SBIRs are short-term. You know, if you're very lucky, you can string a phase 1, a phase 2, a phase 2A and cover 5 years, which is actually a short duration when it comes to fundamental material development, which cycles over a longer period. But frankly, we've benefited through the continued support of our program managers, starting back with Ken Markin and continuing with Helmut Marciska and Donnie Hornback, as well as Michelle Shin. And by stringing that together, it's been able to sustain us, although INCOM continues to operate this particular effort at a loss. The next frontier for us is, well, not to diminish continued need for that SBIR support, but seeding support in among the major programs that might wish to have an LAPPD, but are not explicitly funded to buy one. That hasn't stopped us. My boss teases me when I say that I've discovered it's easier to give them away than to sell them. But you know, if we're making them, we're not going to sit on them, and we're committed to getting them out into the hands of early adopters on the premise that their good results will seed the demand for the future.
Karen, could I follow up on that? This
Yes.
is Henry.
Yes, Henry.
I just wanted to say that what Michael described is very important, because we did very well with SBIRs, but it really is a 10-year thing, not a 5-year thing.
Yeah.
And we're missing one ingredient in this. It's what I described in my talk, which is it's the SBIR is commercialization. I think we're there. We've solved the seal problem. We've solved the photocathode income and solved the photocathode problem. We've got all the pieces. The question is now, how do you start making commodity volume and such? And that's missing. And so I would ask, the CPOD model is a very good one, but I would present this directly to Howard and Company and Helmut. Is there a mechanism? It could be a request for proposals for contracts. It could go to the industry. I mean, it's really an industrial question. But how do you cross the second half of the valley of death? There's a bridge across one half with the SBIRs, but there's another bridge needed, which is to get the cost down, to get the volume up, and to get them enough so that a project that needs hundreds can buy 10 or 20 to really make subsystems to test. Because testing one at a time can tell you a lot. But at some point, you got to be able to make the case to a committee that these are available and consistent and are made with high yield, and you know the cost. And that's not going to happen with the present mechanisms. We need one more mechanism. And so I would put that on CPAD's plate. What do we address to that?
Okay, Howard has his hand raised.
Yeah, Henry, we haven't solved all of the problems, but I think I've been trying to think since LAPPD has been being developed by INCOM. One of the things that we've been trying to think about is how to make it cheaper, to try to make it more like a commodity that some people can buy. And the most expensive part is the microchannel plate. We've been spending a lot of time trying to figure out how to print them, how to be able to do, custom microchannel plates with all kinds of things, and try to develop a market for inexpensive capillary arrays, which have a lot of very interesting properties. Again, this is taking a while, but hopefully in the not too distant future, we will have some progress toward actually being able to make very inexpensive capillary arrays and possibly inexpensive gain stages. And that should address some of the issues on LAPPD, maybe not all of them.
Aaron, one thing that's interesting is how much patience is required, even on the funding agency's part, actually, because here's a project that clearly has, with LAPPD, worked straightforwardly through, but it took a long time. And it's replacing detectors that were fundamentally unchanged since the early 70s, 1970s. And so to expect it to suddenly come to market in a 5-year period when nothing had changed for 60 years is, or 30 years, 40 years, something like that, is I think unrealistic. And so that patience, even, and in particular now with income to make sure that they can learn how to manufacture these is a very important thing in any project like this.
So, okay, let's see. I have Ken Markin has his hand raised.
Yeah, I just wanted to make a comment relevant to the second part of the Valley of Death. So starting in FY21, you will see in the SBIR Phase 2 FOA the option for a Phase 2C. Now, the Phase 2C will provide funding to a small business if they can show matching funds in an equal amount. So this doesn't solve the problem, but it may in the future become one piece of solving the problem. So for an existing Phase 2 or Phase 2A holder, they can apply for a Phase 2C and win an award that's equal to an amount of matching funds they can show to address commercialization efforts.
Okay, so Henry, is your hand up or is that left over? I think that might be left over. All right, so I don't have any new questions. Here was a question that we had written, and so there are problems that were solved in the LAPPD, and you can say that some of them could not have been solved without a multidisciplinary collaboration. So they're seated in the LAPPD from the very beginning was this multidisciplinary aspect, which is really what this whole workshop is about. And making sure, that thrives and that you're able to sort of bring that different expertise together is key. And I just was wondering if someone could kind of speak on how that kind of, how you see that emerging here and what young people how they can kind of repeat this with their problems.
Karen, I would only say that as a chemist learning to navigate my way in this field of high energy physics and nuclear physics, our customers constantly remind us when we talk about a detector that what we make is not a detector, it's a sensor, and it's a sensor that goes into a much more complex system that they refer to as the detector, which might involve radiation, high energy beams, magnetic fields, and all of the rest of it. So I kind of feel like the multidisciplinary approach continues to be pushed or promoted, if you will, from the customer side, who continually ask for more and better. And what we're also seeing, and I alluded to it when I spoke, but didn't have opportunity to go into any detail, is that other companies, independent companies, are recognizing the potential impact of LAPPD, and they're independently developing, well, semi-independently, we collaborate with them. For example, the electronic readout boards, and it's the system approach which is really going to revolutionize these large detector systems at the big experimental sites, and the ability to, reduce the power consumed by these devices, which can be pretty overwhelming, simplify the wiring systems, get the data out without regard to magnetic fields and/or radiation and so on. So the sensor is not enough, and it's really the system approach that we're learning is key.
That sort of leads us into this question on how much customization is needed in order to meet your particular experimental needs.
So actually, my comments on that would dovetail really nicely with what was just said, in that I think our experience was less about customization of the LAPPD itself, although certainly we wanted to make sure that the devices met a certain spec in terms of their performance. But really, it was about developing and customizing all the auxiliary electronics that was needed, both to make sure that we could effectively read out the LAPPDs, and also all the work that we had to go through to figure out how to deploy them in water. And I think that aspect of it, and this issue of developing a system which provides options for the end user and tools that then can be flexibly or easily put together to customize the LAPPD and its as a whole system for our needs, would have, of course, speeded up that process enormously. I remember hearing a comment early on in Michael's talk that they're thinking of putting in more onboard readout on the LAPPDs themselves. And I think one very important aspect of that is to figure out how to keep the built-in pieces flexible so that people can externally customize the device as part of a larger system. But that system aspect of it, I agree, is incredibly important. And that's where all of the customization for us came into play.
I'd like to say something, Karen, just to be devil's advocate a little bit, but I think Howard from the very beginning envisioned an application very much like Annie. I remember seeing pictures of neutrino detectors from the very beginning. And Howard's, because of that vision and some other applications and accelerator experiments and also I think PET and so on, he actually was driven to a very specific design, which was this huge 8-inch, plate, right? But I mean, I think this is, as devil's advocate, I want to say, I think looking at the success of a company like Incom, I think you're going to have to look at other applications, like, for, a biophysics or something. You don't need an 8-inch detector, but you might really have advantages in these very nice, microchannel plates. You might want to be able to figure out a way to modularize, to have different anodes for different applications. So I think rather than trying to solve the whole problem, you're solving the whole problem really for an application. I mean, I think I would argue for more modularity, different cathodes maybe that are optimized for UV and space. You're going to have different requirements, I mean, on forces and so on. So I think I would just, as a devil's advocate, say maybe that is a slight criticism of this approach. That, like, I remember arguing with people about, why 8 inches? Why not 4 inches? 4, is it really? So anyways, I'll just throw that out there.
I see your point, Jim. And certainly that is consistent with what I was saying, that, that original form factor was certainly designed with an application like any in mind. So our customization all came at the other side of things. But it occurs to me that maybe you need both, and ultimately you can't get away from the need to develop different product lines for different applications. it's not clear to me that you can really cost effectively develop a product that will meet everybody's needs out of the box with only a little external customization.
I would add that the time schedule didn't allow for us to go beyond what we refer to as the Gen 1 direct readout strip line LAPPD that everybody's been discussing. But people should be aware that there's a second generation device that's also fairly advanced at this point that relies on capacitive coupling, which is a wonderful concept, which I liken to selling vanilla ice cream and letting the customer put whatever topping on they wish, because the readout is not built-in strips, but rather a printed circuit board that is held directly beneath the tile with an anode that can be customized, whether strip lines are pixelated and whether they're 25 millimeter pixels down to 3 millimeter. So this is a real product that's also becoming available. And there's a third iteration product that we refer to as our high rate picosecond photo detector, which is 10 centimeters, no X spacer, 10 micron MCPs, which probably won't be available until at least next summer. But the pipeline is full of different variants. But you know, the first step on the entrepreneurial ladder is to be successful in commercializing the baseline product that brings in the revenue that helps propel the other concepts forward. So.
I just would like to say I think that was a great answer, and it's probably part of why your SBIR proposals have reviewed so so well. I mean, I think there were two big successes in this thing. I just want to get this out there. The ALD at Argonne was amazing, and what Incom did, it's just how many times does it really, a technology really transfer to a company? So I think that was a great answer.
I have a very forgiving boss.
So is there many instances of industry being involved in a collaboration from the very beginning where you're trying to solve a problem? That is something that was kind of unique here. But so I'd like to hear from Simona. So are you, in your application or in your use of the LAPPDs, do you need much customization, or have you kind of moved towards that? We can't hear you. You're muted.
I was saying I'm a very recent user of LAPPDs. I've only used it for this beam test starting with September this year. From this very limited experience, I would have liked, so the problem was that the detector I used it in, the Cherenkov detector I used it in was placed quite a distance away from the DAQ. So I had to use like really long cables to basically send the signal to flash ADCs. So there was a lot of attenuation of the signal, which is why I couldn't identify the single photoelectron and do a proper calibration of the beam data I got. So all I can show are basically ADC channels of the signal. That's not the case with the MAPMT. For that one, I could identify the single photoelectron to the same type of cables. So I cannot do a one-to-one comparison between my two photon detector options, but I'm working on this bench test, and hopefully I'll be able to do that. So I guess I'm saying I could have used an amplifier really close to the LAPPD, but my detector was in open space. I didn't have the proper shielding. All the electronics was basically far away from the detector behind the shielding wall. So that was, the amplifier was not a practical option for me. So a readout board, if I could have basically digitized the signal at the LAPPD, that would have helped a lot in my case.
Okay.
So Karen, Maurice had asked the question, you know, that there's a large variety of photomultipliers, you know, from huge hemispherical down to just very small, you know, straight on head-on photomultipliers that have a flat photocathode. And will the same variety eventually be needed for LAPPD? And I, you know, in some sense, the geometry of the microchannel plate photodetector is going to be unchanging. It's pretty much a flat device, and that's, you know, the gain structure of the microchannel plates is like that. INCOM has certainly done some very innovative things in producing microchannel plates that are curved, and that's ongoing. But you know, for the photodetector itself, it's pretty much flat. I think the variety is going to be coming in the fact that not every experiment's going to need something that has a 20 centimeter by 20 centimeter active area or something like that. And INCOM now is, you know, going to producing a 10 centimeter device. It may in the future be wanted to have an even smaller device than that for applications. But as Michael, I think, pointed out, you have to produce and establish yourself based on what you're able to produce now with a large area device.
All right, thank you. So we have another question. How groups that work on one aspect of the detector, like the photocathode, to increase quantum efficiency could collaborate with the LAPPD consortia? So how can they get involved and be able to collaborate?
Well, that's something I did, so I'm going to speak up again. So that's exactly where our group came in. We were growing these photocathodes, and what we tried to do was to come up with a transfer technology, and we did come up with one novel transfer idea, which was capping the cathode with indium and then heating it up, and the indium kind of balled up and it restored the cathode and stuff. So there's a very specific answer. You know, we tried that. I think our technology didn't quite fit because it was harder UV, and there were other really good approaches that emerged with the standard multi-alkali cathodes. But I think one of the, this is kind of one of the issues. There's actually a physical transfer needed for a cathode to these sealed tube devices. Sometimes it's a lot easier to grow them in situ, and I think Bob and other people can talk to that, you know, the most successful approaches are probably to do everything in situ. So that's a technical detail, but those kinds of, you know, the devil's in the details. Those kind of technical details can make it difficult, you know, to pull off such a thing. So.
Okay, so I guess we have like about 10 minutes left. So why don't we just go around to the panel and ask them to make any closing remarks or comments. So we start with Howard.
Well, I think that what the community needs to think about, and I'm going out beyond LAPPD at this point. LAPPD is a specific project. There are various details that we've been talking about, applications and so forth. But I really think that people who are in a position to have an overview of where there are real challenges in detectors that are applicable for HEP, for future HEP experiments, not things that are going to be developed specifically for large projects, but things that would make large projects either more effective or cheaper or something like that, to try to identify what those are, to think about how one would go about putting together collaborations to do that, and then to talk to the funding agencies about trying to get some of these things going. I know money is tight in K-25. There are lots of fixed costs and so forth, so there's not a lot of discretionary money. But it really is up to the community to decide where are investments going to have the biggest impact in the high risk, high reward area for HEP in the future, and then try to get these things going. So I think that's really the message that I would bring to the community for the future.
Thank you, Howard. Henry, do you have
Yeah,
closing?
I agree with Howard on that. I must say, I'd like to just address my concern, which is that LAPPD could still fail, and I confess I think it will unless we solve this problem going to the next. There were a number of technical issues raised which actually have been solved. So the seal, the in situ making of photocathodes is solved and patented. The capacitive coupling, we just published a paper that has pads with 300 micron resolution, which are external. So this whole question of can you make one product, the sensor, as Michael Minot said, and then have a separate signal pickup board, and we just patented that as well. And these, of course, are patents by the government, and these are open to research. Nobody pays for them. But this problem of making sure that LAPPD can be produced in quantity, much is made. I mean, the form factor is less important. You can make them various sizes. Once you know how to seal, once you know how to make the plates, you have the ELD. These are the key things. But getting to this next step and supporting income, I just see as incredibly important. And so I would again request that we focus on that. And the new projects, as Howard says, we should think of what we want to, but we mustn't. I would be very sad to see LAPPD go under. Income has been marvelous in supporting a losing effort, losing in terms of money, but somehow we need the second bridge. And Ken Markin's comment was very important. I think that's a very, very interesting and very important thing. So that's my thoughts.
Thank you. Bob?
Well, I think, you know, the purpose here is to sort of generalize some lessons from multi-institution, multi-discipline collaborations. And one of the things that I would second is both Howard mentioned and Ian, you know, that going through something like CPAD, and right now there is an award for young investigators that is handed out yearly, and I think the latest one had 2 winners. They in general would pick one project or something, and these are young people, and I just want to see that encouraged. That is a wonderful thing. You look at the proposals that were coming in under that, and almost every one of the proposals deserved to be funded. They were wonderful ideas, so, you know, my advice, not for young people, but for senior people, is to look to these young people and support those ideas, and provide a mechanism for funding and supporting young people.
Thank you. Mike? Helen? You're muted. There you go.
Thank you. I just, as a generalization, think that you know, strong leadership, starting with Howard and Henry and Bob, made a huge difference here, and that's a really important thing in any of these large multidisciplinary projects.
Okay. Let's see, Jim. Final comments?
Yeah, actually would like to reiterate the point that Michael just made. I think there really was very strong leadership in this project, and I think Bob in particular was saying he wasn't a good project manager. Bob was a great project manager. He was, and I think we should correct that. But I do think, how does this translate to other things? Like for CMB S4, there are all these national labs vying for bits and pieces in the new detector technology and so on. So how does someone for an enterprise that big do what Howard did, which is to kind of pull it all together? I don't have an answer for that, but I think that's something that's been a concern to me, that there has to be some way to pull it together. So there needs to be leadership at both DOE and the funding agencies and the project level. So
Okay. Michael?
Yeah, well, I remain absolutely optimistic about the future of LAPPD, and that does not discount the concerns that were expressed by Howard and/or Henry. In fact, starting this year, 2020, it's no longer just INCOM R&D. We are now the detector business unit, which has the downside aspect of we're accountable for our P&L. The good news is that the INCOM management has been, as Henry pointed out, incredibly patient. But my boss often likes to joke that he can't subsidize the federal government. But it doesn't take a great deal for us to have a sustained baseline business in addition to the great support we get from the SBIRs. Even as many as 50 tile sales a year would help bring us back to a break even. Now, where the big money comes in that Henry or Howard might allude to is nobody wants to see a sustained baseline business. We want to see this thing grow to high volume, and the cost goes down for some of these mega programs. And I agree with Howard and Henry's perspective, is that would take a special initiative. People are not going to buy in volume unless they see a very strong level of validation of the technology, which will only happen when hundreds and hundreds of these units are out in the community. The work that's going on at ANI, the work in INFN, the EIC work at Brookhaven, as this work gets, and Jefferson Lab with the SOLID program, as this work gets published, we believe that will create a wellhead of demand, but it'll grow slowly absent significant government support.
Thank you. Amanda, your closing remarks?
So I think people have said many of the things that I might have said. I would say that it has been a privilege from the beginning to be part of this project, which has seen so much support and leadership and so many amazing creative ideas from the people both on this panel and the other people that have been mentioned. And I hope that we can provide, Michael, that end user result that you need. And certainly we want to see things grow and scale up for applications of much larger scale in future experiments. LAPPDs have a future. We just have to make sure that we get there.
Okay, thank you, Amanda. And Simona, final remarks?
So I think I have two. I would say, as a new user, I wish I would have had the device in my hands prior to my beam test, so I can characterize it and get a feel for it. So if the device cannot be customized, like short notice for me, then I could have customized my test setup. to basically maximize the information I get out of this beam test. But that being said, I would like to thank Michael for extending the loan of the LAPPD I have to do some of the tests I couldn't do prior to my beam test after to try to understand the beam test data. That's what I would say.
Thank you. So I think that wraps up this panel discussion. Thank you all to the panelists and to the questions. And it was a great, enterprise here.
Thanks, Karen.
Thank you.
Thank you.
Thank you,
Thank you for
Karen.
organizing this.
I have an announcement. So for everyone on Zoom, I'm gonna close the meeting and then you'll have to reconnect for the next panel. We have a half an hour break now. And then we'll start with a low background panel. And yeah, see you later.
How much time, Maurice? How much time between you closing it and reopening it?
We have half an hour. The next panel starts in half an hour.
Will you open it a little bit before that?
Oh yeah, absolutely. Yeah.
Thank you.
Need to make the recording with Zoom. Yeah.
Okay.
Thank you, sir.
Thank you. It was